Okay, here in example 4, I want you to state the fundamental theorem of algebra in your own words. And so go back to the beginning of your notes, find the fundamental theorem of algebra, and write something in your own words. And then try to figure out, why do we need it? Why is it important that we have this fundamental theorem of algebra? And if you would like to reach out to me and ask, is your answer acceptable? Then by all means, please do that. I don't want to just tell you how you should state something in your own words. I don't think that's super helpful. And so try this on your own and then reach out to me, and then you can run your answer by me, and I'd be more than happy to discuss it with you. Okay, here in part 2 of example number 4, we want to use the equation and the graph below to do the following. Identify the number of complex zeros that each function has according to the fundamental theorem of algebra, and then by using the graph, determine how many of those complex zeros are real and how many of them are non-real. And so if we look at letter A here, our degree of this polynomial is the 4th degree, and therefore by the fundamental theorem of algebra, I know that this function should have exactly 4 complex zeros. Now, some of those might be real, some of them might be non-real or imaginary, some of them might be repeated, but I know all together they have to add up to total 4. Now, if you look at the graph crosses the x-axis 2 times. And here's a well-known fact, and if it's not well-known by you, then that's okay. Just insert it into your brain and make it well-known by you starting right now. Here it is. A function only crosses the x-axis at real zeros. And so since this red graph, this function, crosses the x-axis twice, that means that I'm going to have 2 real zeros for this polynomial. Now, if there are 4 total and 2 of them are real, how many of them have to be non-real? Yes, very good. 4 minus 2, which is 2. So I'm going to put here 2 non-real zeros, or you could also say imaginary zeros. Okay, in letter B, we have x cubed, and so that's a 3rd degree polynomial. It means that by the fundamental theorem of algebra, we're going to have 3 complex zeros. And if you take a look at the graph, how many times does it cross the x-axis? I see exactly 1 time, and so therefore there is 1 real zero, because functions only cross the x-axis at real zeros. And if there are 3 total and only 1 of them is real, that means 2 of them have to be non-real. Now, I want to point something out just before we move on. Notice that on letter A and letter B, the number of non-real zeros in both cases was an even number. And so the question I would have to ask you now is it possible for a polynomial to have an odd number of non-real zeros? And so hopefully you thought about it for a second, and you realize that no, it's not possible for a polynomial to have an odd number of non-real zeros, because remember, imaginary zeros have to come in pairs. And so that means the number of imaginary zeros must always be an even number. Okay, so sort of along the lines of the question that I just asked you on the previous slide, how many real zeros are you guaranteed to have if you have an odd degree polynomial? Well, let's just maybe take a couple of examples. Let's just say I have a 7th degree polynomial. How many of those could possibly be imaginary? Well, the imaginary zeros have to come in pairs, and so the biggest number of imaginary zeros that you could possibly have would be 6 imaginary, which means that there would have to be 1 real zero. Now, obviously, you don't have to have 6 imaginary. You could have 7 real zeros. But we're just trying to figure out what is the smallest number that we're guaranteed to have for an odd degree polynomial. You could take another example. For example, 21. That's an odd number. So if you have a polynomial that is of degree 21, how many of those at most could be imaginary? Well, the imaginary zeros have to come in pairs, and so therefore the highest number of imaginary zeros would have to be 20, which would leave 1 left over to be real. And so therefore, it seems pretty obvious that you have to have at least 1 real 0. Now, I'd really like to give you one more reason for this, just real quick, and it deals with end behavior. So if you think back to section 2.3 when we discussed end behavior, every polynomial that was odd either went like this at the end or it went like this at the end. Okay, well, if I have a function that looks like this, to go from being down here to being up here, what am I going to have to do at least once? At least once, I'm going to have to pass through that x-axis, which would indicate a real 0. Same thing over here. If I start up with an end behavior up and to the left, and I end down and to the right, that means I have to go through the x-axis at least once. Now, I could go through that x-axis more than once, but I have to go through the x-axis at least once, a minimum of 1 time. And remember that anytime I pass through the x-axis, that is indicating a real 0. And so every odd degree polynomial has to have at least 1 real 0. Okay, number 4 here, for example 4, is it possible to find a polynomial that has a degree of 4 with the given zeros? Explain why or why not. Okay, so for letter A, we have a 0, -3. That's a real 0, so it does not necessarily have to have a pair with it. 1 plus 2i is imaginary, so it's also got to have its conjugate pair with it, 1 minus 2i. And 1 minus I is also imaginary, so it's got to have its conjugate pair of 1 plus 2i. Well, now count how many zeros we have. We have exactly 1, 2, 3, 4, 5 zeros. And can we have a polynomial with degree 4 that has 5 zeros? The answer to that is no, because remember, by the fundamental theorem of algebra, whatever the degree is, that has to equal the number of zeros. And so this guy is going to have at least 5 zeros, and therefore it cannot be a degree 4. Now, what about letter B? If we have 1 minus 3i and 4 plus I, that means we've got 2 more zeros as well. 1 plus 3i and 4 minus I. And if I don't have any more zeros other than that, then yes, it is possible to have a degree 4 polynomial that has 1 minus 3i and 4 plus I as its zeros, because the other 2 zeros would be the conjugate pairs. Okay, here in example 5, we're going to work a fun little problem where I give you some zeros and then ask you to find all the rest of them. And keeping in mind that now in section 2.5, it's possible that we will get some imaginary answers. And so what we're going to do is we're going to take these 2 given zeros here and synthetically divide our polynomial so that we can reduce it down to something that we can solve either with quadratic formula or completing the square, or possibly a different method for solving quadratics. And so I'm going to start by listing the coefficients of my polynomial, starting with x to the 4th. And then it does not matter which 0 you divide by first. I don't really like fractions, so I'm going to do the non-fractional number first. Is that weird for a math teacher to admit that he doesn't like fractions? It's not that I don't like them, it's just I don't prefer them, if that makes sense. So I'm going to drop down the 5, and then multiply 5 times -1, which is -5, and then add, which gives me -2, multiply again times -1, which will give me +2, and add to 3, which gives me 5. 5 times -1 will be -5, plus 3 is -2, and then multiply again by -1, which is going to give me 2, which gives me the correct remainder, and so that's how I know that I did it correctly. Okay, now from that line, I'm going to synthetic divide again by 2/5. And the good news is that this is going to be nice numbers throughout the entire process. So drop down the 5. 5 times 2 divided by 5 is going to give me 2. And then 2 plus -2 is going to give me 0. That's really nice because now 0 times anything is just 0, plus 5 is 5, and now 5 times 2/5 again is 2, and so that again gives me my remainder of 0. And so taking a look here, we started with x to the 4th, We synthetic divided once to get down to x cubed, and then we synthetic divided again to get down to x squared. Okay, so we are now ready to write this last line as 5x squared plus 0x, which I don't really need to write, plus 5, and we're going to set that equal to 0 to find the rest of our zeros. And so pick a solving method. The obvious choice here, in my opinion, since there's no x term, would be square root method. And so I'm going to move over the 5 to make it negative 5. I'm going to divide both sides by 5, which is going to give me x squared is equal to negative 1. And then take the square root of both sides, which will give me plus or minus the square root of negative 1, which I know is I. And so there's two of my answers, positive I and negative I. And then my other two zeros were the ones that were given in this problem, which are negative 1 and 2/5. And before I stop this, I'm going to see if I can erase that and try a little bit better. It doesn't look like it's going to let me, so I'm just going to scratch it out and write 2/5 there. And notice that there are 4 zeros, and this was a 4th degree polynomial. And again, not a coincidence, because we know that the fundamental theorem of algebra tells us that that's supposed to happen. Okay, in the second example, the 0 that I've given you is imaginary, and so I want to bring my calculator in here to just show you how this could be done in the calculator through adding and multiplying imaginary zeros. And so I'm going to start this off just like I normally would by putting my 0 in a box over here and then listing the coefficients of my polynomial, and then drawing a vertical line and going ahead and starting and dropping down the first number, and then multiplying 1 times 2 plus I. Now I know what 1 times 2 plus I is, but I'm going to put it into my calculator because what I want to do is start a running tally here of numbers. And so I'm going to type in 1 times 2 plus I, and that's going to tell me 2 plus I right there. Now, the next thing I'm going to do is I'm going to add negative 4. So with that number still in my calculator, I'm going to subtract 4 and then hit enter. And that's going to tell me that down here, I'm going to have negative 2 plus I. The next thing is to multiply by 2 plus I. So with that number still in my calculator, I'm going to hit times, and then this is where it's very important, and you'll notice that I did it up here as well, but I didn't say anything about it. Now I'm going to say something about it. These imaginary numbers have to be in parentheses, and so just be very careful to make sure that you put them in parentheses. Hit enter, and you're going to get negative 5. And then add negative 4. So again, I probably know what that is in my head, but just to keep my running tally going, I'm going to put negative 9 here. The next thing I'm going to do is multiply by 2 plus I, so times parentheses 2 plus, and then if you're not sure where the I is, if you haven't caught on to where I'm doing that, second decimal point is how you get the I in your TI-84 calculator. Okay, hit enter and you get negative 18 minus 9i. I'm then going to add 36 to that, and that's going to give me 18 minus 9i, and then times, once again, that number in the box over there, my 0, 2 plus I in parentheses, and then enter is going to give me 45, which is going to give me the remainder that I want of 0. Now, let me just say this real quick. Some people get freaked out at large numbers that are imaginary, and they think they're doing things wrong. The way that you know that you're doing something wrong for sure is if you do not end up with a 0 as your remainder. But as long as you end up with a 0 as your remainder here, you know you're doing it correctly. And so don't freak out at weird imaginary numbers until you don't get the correct remainder. If you don't get the correct remainder, then just erase everything, try to figure out where you made your mistake, and then go from there. Now, the question is, where do we go from here? Well, we have to use the fact that if 2 plus I is a 0, I know that 2 minus I also has to be a 0 because they have to come in conjugate pairs. And so I'm going to synthetic divide again, this time using 2 minus I as my 0. So the first thing is I'm going to drop down the first number and then do 1 times 2 minus I, which again, I know what that is, but just to get my running tally going, not 1, but I. Okay, making sure that that's in parentheses, and I get 2 minus I, and so this is going to be here 2 minus I. And then I'm going to add that column. Now I can probably do that in my head. I can see that that's pretty easy and pretty straightforward, so I'm just going to go ahead and do that in my head. I see that both of those things cancel out and give me 0. And then 0 times 2 minus I is 0, plus -9 is -9, and then -9 times 2 minus I can go back to my calculator to do that if I want to. And so 2 minus second decimal to get my I, and that's going to give me -18 plus 9I, which is going to give me the 0 that I want for my remainder. Now, we started with x to the 4th. When we synthetic divided by the first imaginary 0, that got us down to x cubed, and then when we synthetic divided by the conjugate, we got down to x squared. And so therefore this last line says x squared plus 0x, which I don't really need to write, minus 9 is equal to 0. And so to find my remaining two zeros, I'm just going to solve this quadratic. Square root method is probably the easiest way, so add over the 9 and then take the square root to get plus or minus 3. And in addition to plus or minus 3, we also have 2 plus or minus I, which is a total of 4 zeros, which should make sense because this was a 4th degree polynomial.